Welcome to the deep dive. Today, we're making a pretty big leap. We're moving you out of the role of just, implementing a network plan someone else gives you.
Right.
Today, you get to be the architect.
That's it. That's the mission. We're taking the raw requirements. Things like Department A needs 150 hosts, or we need about 75 separate network segments, and we're turning that into a complete, usable IPv4 addressing plan from scratch.
And our source material lays this out as a really methodical progression. It frames the whole thing in 4 phases. It starts with analysis, and then it ends with the implementation. But the real core challenge, the heavy lifting, is in that second phase, designing the subnets.
Exactly. We're going to assume you've already got your address space picked out, a Class A, a B, or a C network.
Okay.
So the focus narrows down completely to choosing one, just a single subnet mask that can meet all your requirements. And it has to be efficient, without a lot of waste.
Yeah, this is where the simple math meets some pretty serious organizational strategy.
It really is.
Okay, let's unpack this. The best way to think about the design problem is to think in bits.
Right.
As the architect, you see those 32 bits of an IPv4 address as 3 distinct parts. You have your network bits, or N, your subnet bits, S, and your host bits, H.
And those N bits, they're fixed.
Right.
If you pick a Class B network, N is 16. That's locked in.
So your job is really to figure out how to split the remaining bits between S for subnets and H for hosts.
And there are 2 hard mathematical boundaries, rules you just can't break that tell you the minimum number of bits you need for each of those.
Let's run through those non-negotiables. So for the subnet bits, the S bits, you need enough unique combinations to cover all the network segments you need. So the formula is 2 to the power of S has to be greater than or equal to X, where X is your required number of subnets.
And then for the host bits, the H bits, the formula is a little different because of those 2 reserved addresses in every subnet.
Right, the network ID and the broadcast address.
Exactly. So the total combinations, 2 to the power of H, isn't enough. You have to subtract 2. So it's 2 to the H minus 2, and that has to be greater than or equal to Y, the number of usable hosts you need.
Now, this brings us to the absolute limit of the whole system. We know that N plus S plus H cannot be more than 32.
Right. There are only 32 bits.
So what happens if you calculate the minimum S you need and the minimum H you need, and you find yourself needing, 33 or 34 bits total?
That is the hard wall of IPv4 design.
Yeah.
And the source has this great kind of depressing example. Imagine you've been given a Class B network, so N is 16.
Okay.
But your requirements are tough. You need 300 subnets, and each one of those needs to support 280 hosts.
Okay, let's do the math on that really quick. For 300 subnets, 2 to the 8th is 256. That's not enough. So you need 2 to the 9th, which is 512.
So S has to be 9.
S is 9 bits. And for 280 hosts, again, 2 to the 8th minus 2 is 254. Also not enough.
Right.
So you need 9 bits for hosts as well, which gives you 510 usable addresses.
And there it is. Your total necessary bits are 16 for the network, plus 9 for the subnets, plus 9 for the hosts.
That's 34.
It's 34. And since 34 is greater than 32, the design is impossible. It fails right there. You cannot do it with a single Class B network.
And that's such a critical takeaway. When your N, S, and H bits add up to more than 32, you have to go back to the drawing board entirely.
You do. You either need a bigger address space, which is, basically impossible, or super expensive these days.
Or you're forced into more complex tools like VLSM, or maybe this is the moment you finally have to start planning your move to IPv6.
That check is always the very first thing a designer does.
Okay, so let's look at the much cleaner scenario. The one where the design gives you exactly one solution.
This happens when your minimum required bits add up to exactly 32.
Let's use that Class B network again, N equals 16. But this time the requirements are a bit more reasonable. Maybe 200 subnets and 180 hosts per subnet.
Okay, so for 200 subnets, you need 8 subnet bits. That gives you 256. For 180 hosts, you need 8 host bits, which gives you 254 usable IPs.
And if you add that up, 16 plus 8 plus 8, that's exactly 32.
Yep. The math just locks you in. There's only one possible mask that works. And you find it by adding N plus S, so 16 plus 8 is 24. Your mask is a /24.
You have 0 strategic choices to make. The math just gives you the answer.
Exactly.
But the really interesting part, I think the part where you actually have to make a decision, is when there's wiggle room. What happens when we calculate our minimum N, S, and H, and the total is less than 32?
That means we have spare bits. And for every single spare bit, we get a choice. Do we assign it to the S column to get more subnets or the H column for more hosts?
And this is really the core of the design challenge, isn't it? Because that decision basically sets the growth plan for your entire network.
It absolutely does.
Okay, so let's use the main example from our source material. Class B network, N is 16, and we need 50 subnets and 180 hosts per subnet.
All right, so 50 subnets. The minimum number of S bits you need for that is 6. 2 to the 6 gives you 64 subnets.
Okay, S equals 6.
And for 180 hosts, we already know that one. Minimum H is 8. That gives you 254 usable IPs.
So let's add it up. 16 plus 6 plus 8. That's 30.
30. We only needed 30 bits, but we have 32 available. That means we have 2 spare bits to play with.
And 2 spare bits means we actually have 3 different valid subnet masks we could choose. And the choice between them isn't really technical, it's more of a business decision. So how do we find what those masks are?
We find the boundaries, the 2 extremes. First, the shortest possible prefix. This is the mask that uses the absolute minimum number of subnet bits required.
So in this case, just 6 S bits.
Just 6. So the prefix is N plus S. 16 plus 6 gives you a /22.
A/22. Okay, so that uses 6 subnet bits, which leaves 10 bits for hosts.
And 10 host bits is huge. That's 2 to the 10th minus 2, which is 1,022 usable hosts per subnet. Massive capacity.
Right, and what's the other boundary?
The longest prefix.
Okay.
This is the mask that uses the absolute minimum number of host bits. It maximizes your subnets. The formula here is 32 minus H.
So 32 minus our required 8 host bits gives you a /24.
Exactly. A /24 uses 8 subnet bits, which leaves you with the 8 host bits you need. It meets the host requirement exactly, but it maximizes the number of subnets you can create.
So our valid range of choices is /22, /23, and /24.
And that's the decision point. So I'll ask you, if you're the architect, why not just pick the /22 every time? I mean, more host capacity is always good, right?
It feels like the safest choice, doesn't it? But I guess the problem comes down to efficiency and, planning for the future.
How so?
Well, if you pick the /22, you only get 64 total subnets out of that whole Class B network. And, maybe more importantly, even if one department only needs, say, 10 hosts, you're still giving them a whole subnet with room for over 1,000.
That's a colossal amount of wasted addresses.
A huge waste. So 63 of your departments could be wasting almost all of their address space.
That's the insight right there.
Oh.
Choosing the shortest prefix, the /22, means you are prioritizing dense growth in your current departments. You get massive host capacity, but you burn through your subnets fast and you waste a ton of IP addresses.
And on the flip side, if you choose the longest prefix, the /24, you're conserving your subnets. You give up that extra host capacity. Every segment is capped at 254 hosts.
Which is still enough for our requirement of 180.
Right. But you gain 4 times the number of possible subnets. You go from 64 total to 256.
And that choice, choosing the /24, it's a bet. It's a prediction that the company is going to grow horizontally. It's going to add lots of new departments, new labs, new offices, even if each of those new locations only has a moderate number of devices.
So the /24 is all about strategically protecting your subnet IDs for the future.
It is.
Which means the /23, the one in the middle, is sort of the balanced approach. It splits those 2 spare bits. One goes to subnets, one goes to hosts.
Yep. You get 128 total subnets and about 510 hosts per subnet. It's often the default choice when the future is really, really unknown.
But a great designer is always going to ask that question. Where is the real risk? Are we more likely to run out of IP addresses within a department, or are we more likely to run out of new segment IDs for new departments?
And that risk assessment is what should drive your final choice of mask.
So once that big strategic choice is made, let's say the company decides to prioritize future growth, and they choose the /24 mask to get the most subnets, the next step is purely mechanical. You have to translate that mask into a definitive, usable list of every single subnet ID that's now available to you.
And we always start with the 0 subnet. This is the numerically lowest subnet ID, and it's always identical to the original classical network ID you started with.
So if our network was 172.20.0.0.0, our very first subnet ID is 172.20.0.0.0.
That's it.
The source material has a pretty interesting historical note on that 0 subnet. For a long time, it was actually avoided.
Yeah, that's true. The thinking was that when the subnet part of the address was all binary zeros, some older routers could get confused and not be able to tell the difference between that first subnet and the entire unsubnetted network.
So engineers would just not use it to be safe.
They would, yeah. But today, I mean, virtually all modern hardware and software, especially Cisco iOS, defaults to allowing it.
Yeah.
There's a command, if in subnet 0, it's on by default. And you want to use it because it maximizes your desk space.
Okay, so to list out all the other subnets, we need a shortcut. We need something faster than counting in binary.
And that's the magic number. It's a really simple decimal math trick.
So how do you find it?
First, you find what's called the interesting octet. That's the octet in your subnet mask where the boundary between the subnet bits and the host bits falls.
It's the octet with a value that isn't 0 and isn't 255.
Exactly. So let's use a quick example. If we had chosen a /22 mask that's 245.255.252.0, the interesting octet is the third one, the 252.
Okay.
The magic number is just 256 minus that value. So 256 minus 252 is 4.
And 4 is the pattern. That's the magic.
That's it. It tells you that your subnet IDs are going to increment by 4 in that third octet.
So you start with the 0 subnet, 172.2.0.0. The next one is 172.20.4.0, then 172.2.8.0, and so on.
All the way up. And you just stop when the next jump would hit 256. That previous number is your last usable subnet ID. This little trick gives you a super fast, formal way to generate the whole list.
But that works great when all your new subnet bits fit neatly inside one octet, right? Like when you have fewer than 8 of them. What happens with a more complicated mask? Like what if we had that Class B network, but we needed 10 subnet bits? That would be a /26 prefix. Now those 10 bits are spread across the third and fourth octets.
Right, and for this we need a slightly expanded process. We need 2 new terms. We still have the interesting octet. That's the rightmost one that has subnet bits in it, so the fourth octet in your example.
Okay.
But we also have the just left octet, which is the one immediately to its left, so the third octet.
So how does the pattern work when it crosses that boundary?
The magic number is still calculated only on the interesting octet. For /26, the mask ends in 192. So the interesting octet, the fourth one, is 192.
So the magic number is 256 minus 192, which is 64.
64. So the pattern of increments in that fourth octet is 0, 64, 128, and 192.
But wait, we have 10 total subnet bits, so we should have 2 to the 10th or 1024 subnets, not just 4.
Exactly. And this is where the rule changes. It becomes about block repetition. You list out those first 4 subnets with a just left octet, the third one set to 0.
So 172.0.0.0.0.0.64 and then 0.192.
And that completes one block of 4 subnets.
Ah, I see. So then you increment the just left octet by 1 and you just repeat that entire 4 subnet pattern again.
Precisely. The next block would be 172.1.12, 172.2.1.64, 1.128, and 1.192. And you keep doing this, incrementing that third octet all the way up to 255.
And that's how you mechanically generate the full list of 1024 subnets. It's the final step, really, in turning that big strategic choice into a concrete executable plan.
That's the whole process.
So today we've really gone through the whole journey from getting a raw requirement from the business all the way to a final network inventory. The essential takeaway for me is that network design is all about balancing those 2 formulas, the minimum S bits and the minimum H bits, and then recognizing that your final choice of mask is really a prediction about the future.
It is. We saw that the choice between the shortest prefix, which maximizes host capacity, and the longest prefix, which maximizes the number of segments, that choice often determines how long your address space is even going to last you.
The math just gives you the options. The architect has to use their judgment.
Exactly.
So here's a final thought for you to chew on. Imagine a large company is going through a big merger. They want to give each of the newly combined departments their own subnet ID for, security and simple administration.
Okay.
We know that maximizing the number of subnets, choosing that /24 over the /22 in our example, it limits the host capacity for every single one of those departments.
Right.
So what kind of organizational pressure, or maybe even a regulatory mandate, might force an engineer to prioritize that administrative separation over having massive but probably unused host capacity? That choice, the risk of running out of subnet IDs versus the risk of hitting a host limit in one department, that requires thinking way beyond just the pure math.